There are two primary processes: 1. Transaction management, and 2. Concurrency control in database management systems. Transaction management, or TM, handles all transactions properly in DBMS. Database transactions are the events or activities such as series of data read or write operations on data objects stored in database system. Larson, Blanas, Jaconu, Friedman, Patel, and Zwilling, 2011. Concurrency control, or CC, is a process to ensure that data is updated correctly and appropriately when multiple transactions are concurrently executed in DBMS. Connolly and Begg, 2015. In general, concurrency control is an essential part of TM. It is a mechanism for correctness when two or more database transactions that access the same data or data set are executed concurrently with time overlap. According to wikipedia.org, if multiple transactions are executed serially or sequentially, data is consistent in a database. However, if concurrent transactions with interleaving operations are executed, some unexpected data and inconsistent result may occur. Data interference is usually caused by a write operation among transactions on the same set of data in DBMS. For example, the lost update problem may occur when a second transaction writes a second value of a data content on top of the first value written by a first concurrent transaction. Other problems, such as the dirty read problem, the incorrect summary problem, are also identified in the Connolly and Begg's textbook. There are two main kinds of concurrency control mechanisms: the pessimistic or conservative concurrency control and the optimistic concurrency control. The pessimistic concurrency control delays the transactions if they conflict with other transactions at some time in the future by locking or a timestamping technique. According to Kung and Robinson, 1981, the optimistic concurrency control that assumes that the conflict is rare allows concurrent transactions to proceed without imposing delays to ensure serializability, then check conflict only at the end when a transaction commits. Notice that there is another mechanism, semi-optimistic technique, which uses lock operations in some situations if they may violate some rules, and does not lock in other circumstances. Both pessimistic and optimistic concurrency control mechanisms provide different performance. Example, the different average transaction completion rates or throughput, depending on transaction types mix, computing level of parallelism, and other events. According to Vallejo, Sanyal, Harris, Vallejo, Beivide, Unsal, Valero, 2011, there is a trade-off between the concurrency control techniques. Their pros and cons are shown as follows. For pessimistic concurrency control, the strength is guarantee that all transactions can be executed correctly. Data is properly consistent by either rolling back to the previous state, abort operation, or new content, commit operation, when the transaction conflict is cleared. Database is relatively stable and reliable. Its weakness is transactions are slow due to the delay by locking or time-stamping event. Runtime is longer. Transaction latency increases significantly. Throughput, or the amount of work, example read, write, update, rollback operations, etc., is reduced. For optimistic concurrency control, the strength is transactions are executed more efficiently. Data content is relatively safe. Throughput is much higher. Its weakness is There is a risk of data interference among concurrent transactions since transactions conflict may occur during execution. In this case, data is no longer correct. Database may have some hidden errors with inconsistent data. Even conflict check is performed at the end of transactions. Transactions may be in deadlock that causes the system to hang. Many users often encounter the data interference issues in database management systems in stock markets. The simple example addresses the inconsistent data issue as shown as follows. Multiple analysts or investors from Fidelity Investments, LLC, access a client's fund in a database for stock trading from either Dow, bonds, or mutual funds. Both analysts A, B, perform some transactions to transfer some amount of money to buy stocks from different funds for their daily works. In this scenario, the nested transaction is used in database. At scheduled step T7, a transaction manager faces inconsistent data. That is, $800 or $1,000 in the client's balance. The operating system can execute either thread A for a balanced result of 1,000 or thread B for a balanced result of 800. Either case, the balance content is incorrect. For pessimistic technique, the transaction B may be delayed for a long time or in a deadlock. For optimistic technique, it goes through with incorrect data in the database. Furthermore, the micro-execution of the software threads is unknown, ambiguous, and out of control. Database is in the unknown state.